So
do any fun over the weekend? Not good.
My band played a show at Valor.
Wow,
That was pretty fun.
very cool. What's your band called?
Samuel Charles Band.
What?
The Samuel Charles Band.
Samuel Charles. Wow.
yeah.
I've been there. That's the one downtown Provo?
Yeah.
Yeah. My son played a part in, there was a battle of the bands, maybe in the last semester or something. Yeah. My son played a part in one of the songs for one of the bands.
It's a nice venue.
Yeah, it was cool. You could tell the parents of the band members. They're like the old people sitting on the side. They were easy to pick out. So, yeah, very cool. Anyone else have any fun news?
I said soccer.
Oh, I was good. Okay, soccer. Playing, watching, playing. Hey, yesterday it felt like spring. Like the first day was like, wow, it feels more like spring than winter. It feels that way today. Oh, we still need more snow. Go to the mountains. So,
I'll take rain over snow.
we'll break down. Well, the mountains need snow. We can take rain in the valley and snow in the mountains. So we can do that. What, are you from Seattle or something?
No.
Oh. All right, who'd like to start us off with a prayer? Thanks.
Together again today. And for opportunity to be here at this university. All the blessings which thou hast given us in our lives. Give us a blessing with the math professor and TA that they have the time to do everything else they need to do in their lives. Learn these principles. And that they'll be blessed for their help that they give us. Blessing upon all of us that we can have the Spirit to be with us today as we learn, that we'll be able to remember these concepts and apply them. And be able to prepare sufficiently well for the tests upcoming. And we'll be able to do well. It's tough. Since we ask them for Jesus Christ.
Amen. Thank you very much. Just a reminder, throw on your masks and as soon as you walked in and realize you were in class. Hey, really quickly on this first one, what's the strategy you read about or we talked about on the video about how to find the inverse of a matrix?
Put the identity matrix on the other side as an augmented matrix.
Okay, so augment it with the identity matrix.
And then you solve.
Solve, meaning we'll reduce this side.
Roller
You're
slide.
reducing the whole thing, and you're getting the left side to be into the identity matrix.
Put it into reducer echelon form.
If reducer echelon forms the left side, and then where's your inverse matrix?
It's going to be whatever's on the other side.
Yeah, it's going to be the one on the right hand side that you end up with. So, the one way to make sense of what you're doing, we talk a little bit about matrices and transformations, and we'll have a whole section on that later on. But this, every time you do a row operation, like this matrix, you can think about as doing a lot of transformations to three-dimensional space. And every time you do a row operation to reduce this back to the identity matrix, you're undoing one of those transformations. And so when you end up with on the right-hand side is the matrix that undoes all of those transformations. So it's kind of like one way to think about what you're doing. So this is very, very common problem. I think probably every single one of the practice exams that are up online for this upcoming test have a problem like this on it. This is a nice problem on the exam because you can test to see whether you get the answer right. How do you test? Yeah, you just multiply with what you got for the inverse with this, and if you don't end up with the identity matrix, you know you did it wrong. So go ahead and just try to find your find your error or do it again. So, okay, and then write down the elementary matrix that corresponds to the first row operation you used up here. Use the inverse from this to solve this system, and then you can use the inverse for finding the inverse that system, the solution to that system too. So I'm going to turn you guys loose and let you work on those for several minutes. You've got questions, go ahead and raise your hand, work with the neighbor, as always.
Yeah, I have a couple questions here.
So do QR factorization. I mentioned it a little.
Try to focus a little bit more.
Hit a few.
Go back to like the edge.
When we get working on to tell you. Oh, to do it.
So they had like. Now they're like
Behind it.
It was just like climbing up the cedar.
Send me some feedback. Like send me. Some feedback.
Wasn't the only one. It's a big step, I think. Like that's the I think this kind of they can watch them both.
Why have that handwriting? Read them both. Work with that.
Add 4, subtracted 4. Every time I do that. How do I do that again? Answer, but then you forget again and you gotta relook at it. The same video. Like Conic has. Solve it.
I'm going to be taking down this slide. If you want to snap a picture of it.
Yeah, it's funny.
It is already uploaded on the Livingston
Wait for completion, we actually do right.
Okay, I kind of know that, but then you get to number 3, so. I know. The ball. I didn't check it. So much harder. It's not hard to fill it out 'cause it's all lessons here.
I'm trying to check what the inverse is.
Yeah.
I'm having code, so I don't know. What's that? You trying to check
Oh, wait, that's not.
according to- Yeah. This is the inverse, but
That's really what I thought.
I work it through, so yeah, I don't know how it works. I showed up a little late.
I mean, it's like. Somewhere I just flipped some negatives.
What did you end up with?
Like, I haven't. Sure.
Like your last row.
Oh, the middle column.
No, just notice that.
Okay, so I did something wrong.
What do you say studying? Well, I'm not even this first year, so if I come for that. You can do that?
It was easy until last week, and I was like, oh.
Okay.
So that,
Some of the concepts are a little bit. Real number right now.
And then I didn't have any problem on Saturday or on Monday, so I just could be on.
okay.
On Saturday.
Questions? A few announcements. Before we move on. Exam this week, exam number 1, Wednesday to Friday in the testing center. Oh, I didn't change those dates. Those dates are wrong. The Wednesday and Friday is correct. In the testing center, after 2 o'clock, start to cost you money. Also, it's the exam covers all material up through 3.3, so that's what we're finishing up today. Okay. On inverse functions. There's no calculators or notes or anything else on the exams. Just you, a pencil, and scratch paper. It will be similar format to the practice exams that are already on Learning Suite. Highly encourage you to go through as many of those as you can. If you're comfortable with all those problems in that material, you'll be just fine. It's supposed to be a 2-hour-ish exam, maybe a little bit longer, but because it varies so much, you might want to time yourself taking one of the practice exams. It's good practice for the exam, but also kind of gives you an idea about how long it takes you. Yes.
There's multiple choice.
Multiple choice and free response. So there's all of the practice exams, I think, are that way. It's pretty much the same. And it says tomorrow. It's supposed to be. Tomorrow is in the next class period. So Wednesday we'll have a review day in class. So you're welcome to, it starts Wednesday. Sorry about this. It should work out ideally because we're reviewing late on the first day when you could take the exam, which shortens the time period. If you want to have if you want to fit in on the review before you take the exam. Give me a warning now. We will be reviewing for the exam on Wednesday. Questions about the exam? It's not time. Right on. On a bubble on the sheet. On the, to the right. Yeah, there won't be a separate scan trophy.
Other questions? What I have in my cup? Okay. All right. So here's some work. So it's pulled from another student in the previous class. You can compare yours to this student's work. You may have done different row operations. You may have started differently, but inverses are unique. If this is an invertible matrix, there is only one matrix that I can multiply by this and get the identity. So you have to end up with that exact same thing. Okay? Even if you did different steps or the steps in different orders to get there, there's not another option. Okay. So in this one, you can see we augmented with the identity matrix. This student for the first row operation took a -1 of the first row. I'm sorry, -2 of the first row and added to the second row to get this 2 to be a -2, to get this 2 to be 0. So -2 times the plus the 2 gets 0. -2 plus the 0 gets the -2. -4 plus the 1, -3. -2 times the 1, -2. Okay, we won't go through all of those, but I snapped this right before she was testing. She was testing to see if she got the right answer. I took the picture before she finished, but you can keep going. 0, 2, 2. So if we want the third row here, we can take the third row here, dot it with this column. First one's a 0, so I don't have to worry about that. I get a -4 plus 4, that gets me a 0. 0 to 2, 2, dot this column. 0, then I have 2 and a -2, that adds to 0. And 0, 2, 2, dotted with this column, you get a 0. I get a 3, and I get a -2. 3 minus 2 is 1. So it all works out. Pretty tedious. It just turns out it's a hard task to find the inverse of the function. If you have like a seriously sized matrix, you know, 100, 100, 200, 200, 200 by 200 range, like computers might take 1,000 years to do that. And it's just like atrocious how many calculations it takes to use this process to find the inverse of the matrix. Yes.
How do I phrase this question? So if you have A and A inverse, is the inverse of A inverse A?
Yes, good question. Yeah, so if you have A and A inverse and you're trying to find the inverse of A, sorry, you're trying to find the inverse of A inverse, is it A? Yes, it's A. That's the one matrix you can multiply. You can multiply here by this matrix and get the identity. The only one is this.
Therefore, it doesn't matter if you multiply left or right.
That's right. It doesn't matter if you have a matrix and its inverse, they do commute. That's one of the situations where they do commute. So it doesn't matter if you have A times A inverse or A inverse times A. Nice thinking. Good job. Yes.
For the 2 by 2, there's like a formula. Does this also work?
So for the 2 by 2, there is a formula. Later on, we will learn a formula that you can generalize that 3 by 2 one, but it turns out to be pretty much harder to do for 3 by 3 and beyond, where it's usually quicker to just do this.
So can we use this way for the 2 by 2?
Yes, you can do this way for the 2 by 2 also.
They're all on the square.
Yes, this technique works for all square matrices. Yeah, once you get so big though, it just takes. Okay, other questions? Hey. So the next, number 2, write down the elementary matrix that corresponds to the first row operation used in 1. So we'll go back to that question, but quickly, elementary matrices, there's 3 basic kinds because there's 3 basic row operations. Each kind represents one of the valid row operations we can do. This would add a multiple of row 4 to the first row. Sorry, this would make your new 4th row. You would get 4th row. We got 3 rows. Your new 3rd row would take 4 times the first row and add it to the 3rd. So this is the kind of structure you'd end up with. One of these non-zeros being a non-zero. One of these zeros being a non-zero. That's the structure for adding a multiple of a row to another row. This corresponds to swapping rows, and this corresponds to multiplying a row by a non-zero constant. Yes.
And so that's also what we'll get on the right hand, the augment, when we're doing that row operation, right? It's like from
If you just do like one of these moves the very first time, then actually what you get on your identity matrix over here that you started with, you do one row operation, what you get is an elementary matrix that corresponds to that. Okay. So
another thing is like the inverse of the matrix is the product of all the elementary matrices required to get it to the identity matrix. Right?
That's right. Yeah, we'll talk about that. We'll dive deeper in that in just a second. So so in this one, what is the elementary row operation to that corresponds to the first move here? Sorry, the elementary, not the elementary row operation. It's been a long day. Okay, elementary matrix that corresponds to multiplying this row by a -2 and adding it to this row. It's this one right here. So if I were to take this matrix and put it over here and then multiply it by this, then when I do this multiplication, I will end up with this matrix. And really, the only thing that's changed is the second row, right? Because if I have 1, 0, 0 over here and do that multiplication, I just get the first row that's repeated. Same thing with 001. When I take the 001 and I do that multiplication to get my new third row, then I just duplicate the third row. But the only thing that's different is this is a second row. I have a -2, 1, 0. So when I do that multiplication, I get a -2 times this plus one of these, and that becomes my new, my new cell. And -2 times 1 add together. -2 times 1 add together. So this is our elementary row. That's our elementary matrix for that first row of operation. Okay. In practice, we actually don't calculate row elementary matrices. You could, but they are powerful for mathematicians because they're powerful theoretically, which means you can use them to reason through problems and you can use them to write proofs. So they're ways to justify things that have to be true. So I'm going to give you a challenge. A theorem in the book states that a matrix is invertible if and only if the matrix can be written as a product of elementary matrices. So if you know you have an invertible matrix, then you know you could rewrite it as a product of elementary matrices. Elementary matrix times an elementary matrix times an elementary matrix. And it's if and only if. So if I can write a matrix as a product of elementary matrices, then I know it's invertible. So can you use that theorem, use that fact? How could you use that to reason about the product of two invertible matrices? Is an invertible matrix times an invertible matrix always invertible? So I want you to think about that. And if you think it's yes, how would you prove that using this idea? Okay, using the fact that invertible matrices can always be written as a product of elementary matrices and vice versa. Okay, so think about that. How would you argue? How would you argue one way or the other about this invertible matrix times an invertible matrix is an invertible one? You're welcome to work with any of those.
Two matrices put together. Elementary matrices. You know, there's a bunch of other. That's the problem.
Should be able to proof. You like looking at there?
I mean, I feel like it did.
Saying
not-
that
Well, I guess
matrices can.
it makes sense because to write each matrix as a product of matrices. Then it's just a product of all these elements. Right, so it's still invertible. Have like more elementary matrices. Like if you need like three,
Two matrices
to
that.
get to the one, and then like 7 of them just to get the new.
Or if you can. The product of some three matrices. Yeah, I think EA1, EA2 to EBN, 1EB2 to EBN, AB is EA1, EA2, EB1, EB2 to EBN, and it's that's also the product of elementary matrices.
I was thinking it was, you know, non-invertible matrices.
So,
Yeah. I don't know why. Because when I hear invertible, like the prefix makes it sound like not.
yeah. Oh, I get exactly.
So I was like,
Not vertical.
matrices that are not invertible. And so I was like, how can I prove that if they're not invertible, that how would they have to prove that?
Solution with the product. I mean, so
Actually,
two non, it's because it's a type of metric. Which also
no, you totally, yeah, you totally.
function. That's the definition of it, but I don't know. That
Where's this is also.
playing
But,
group of elementary. Yeah.
converse, inverse, and counter positive.
What?
Which would also mean it's.
Yeah.
So assume that A is invertible. Have A times some product element matrices, but A is not the product element matrices, therefore the product is not invertible. Is it? If B also isn't,
I got 8.
they could equal an elementary matrix.
Another inverse.
I'm not sure. But
that's where I was.
if one of them is invertible and the other one is not, then the product is definitely
Not
invertible.
So
So I was just confused because I was like, if they are not elementary matrices, can non-elementary matrices be combined in order to do elementary matrices?
Neither.
I didn't know how to do that. That's why I was-
Well, if you have some elementary matrices equal to some AB, or AB are not invertible, then do stuff like this. So
oops, that was.
you can barely perform operations if they're not
It doesn't even not have two invertible states.
I don't know. Still trying. Still got 30.
It's combined. to
Nope,
create
hold on. So why? Why? So if you have some matrix C that is invertible, switch to
Right. It's like. Yeah.
then you can switch to C.
Okay. So I've heard
Oh,
And they wouldn't be able to.
a few arguments related to, well, let's think about A and B. Well, so if we think it's true that invertible matrix times invertible matrix is always invertible, but I might start by naming invertible matrix, the invertible matrices that I'm starting. So I have an A times a B, and if I can write each one of those as a product of elementary matrices, then A times B can be written as all the elementary matrices that represent A and all the elementary matrices that represent P, and I'm multiplying all those together. So now I've written the product as the product AB is a product of elementary matrices. So I know that it must be invertible because this goes either way. If it's invertible, I can write it as a product of elementary matrices. It's a product of elementary matrices, it's invertible.
If A and B are not invertible matrices, does that imply that their product is also not invertible?
Yes. So once you have one non-invertible matrix in a product, it's not invertible. Like that product, the result is not invertible. So,
Are matrices, or not matrices, elementary matrices, those unique?
are elementary matrices unique?
Yeah.
Yeah, for like one row operation, for a particular row operation, there's only one elementary. There's only one elementary matrix.
So each matrix has a, just for sake of brevity, representation.
Yeah, you could, yeah, you think about it that way. Although it's unique if you have to specify what order you were doing the row operations
Okay.
for it to be actually unique, because we could do different row operations or different row operations in different orders. But if you specified like, I'm always going to do this process, or do it in this way, then you could do that.
So
Yeah, go ahead. Yes, all the elementary matrices are invertible. So that's it. So that's it. Yeah. How can we see that? Well, if we come up here, what's the rank of this matrix? It's 3. It's full rank. If I row reduce, I have the identity matrix. Okay, what's the rank of this one? Or how many pivot columns do I have? 3. each of these is invertible. So this was the argument that I heard just written up, where I'm going to take two matrices. What if I take two invertible matrices and then I multiply them? Well, I can write them as a product of elementary matrices. So hey, I'm going to write E as a bunch of elementary matrices, B is a product of a bunch of elementary matrices, then AB is just this long product. Well, they're all elementary matrices, so now I know AB is a product of elementary matrices. So then it's got to be invertible. So one of the key points here, row operations, if you start with an invertible matrix and you're doing row operations, there's no row operation that you can do or series of row operations to turn that into a non-invertible matrix. And the other way, if you have a non-invertible matrix, when you do row operations, no matter how many you do, there's no row operation or series of row operations that can turn it into they can turn a non-invertible matrix into an invertible.
So if we're thinking about matrices as transformations on a plane, like you're saying that there are some transformations that you can't undo.
Yes, that's exactly right. Let me see if I have. Let's see if Bart's up here still.
There's information.
Oh, he is up here. So that, for those in the back who may not have heard, if we're thinking about matrices as transformations, then that means there's some transformations you cannot undo. So yes, that is right. So for example, here's okay, so let's get a non-invertible matrix here.
Doing row operations.
So here's 1, 1. And now I'm going to change C. I'm going to change C right here to make this a non-invertible matrix. What's the number I could put here to make this a non-invertible matrix? 1. Because then I'd have linearly dependent columns or linearly dependent. Okay. So let's watch what happens here as I get C to 1.
Yep, exactly.
So what that operation does is it collapses the whole plane onto a single line. And there's no way, so infinitely many points ended up, it took infinitely many points that ended up at one point on that line. And there's no way for me to undo that. I don't know where all of those, I just know, hey, they went to this point, but I don't know where they started at. So it's not, I can't undo that transformation. Or there's infinitely many transformations that I could do to get them back, and I don't know which one it was.
So in that case, the determinant being 0 basically describes a loss of information made during the transformation?
Yes. Yep. So the determinant of 0. Yeah, well, yeah, there's really nice geometric connections to the determinant, which we'll talk about later when we dive in. But yeah, it corresponds to a loss of information. An invertible matrix, you can just think about an invertible matrix. The multiplication by an invertible matrix is that there's no information loss. You just did something, you can get all that back. So.
There exists a lot more invertible matrices than like non-invertible matrices in our vector span.
They're both infinite. Yeah, they're both infinite.
Are they both uncountably infinite still?
And yeah, they're yeah.
Well,
So
yes. Well, I mean, if you think of it like this,
so if you ask the questions, if I randomly put in, we'll just stick with a 2 by 2. If I randomly pulled 4 numbers from maybe a uniform distribution from 0 to 1 and put them in there, what's the probability of getting an invertible matrix?
Yeah.
Probability is pretty high.
Okay.
So I think you're more likely to have an invertible one than a non-invertible one for a 2 by 2, because you'd actually have to end up with one column being a scalar multiple. So, yeah. Okay. I'm glad you asked that question. I didn't actually get to show Bart collapsed to nothing in the earlier class. So, All right, so really quick. The invertible matrix theorem, I believe this was pulled from, I think I pulled this from the slides you've already seen on the video, but just want to clarify. Like the one in the book only had like a list of 5 things. This one has more. Each of these is equivalent. If you know one of these, then you know all of the other ones. Okay. So if A is invertible, then you get all of these things. You know, it's equivalent to the n by n identity matrix. It has n pivot positions. This is really, I didn't put this one in there. The rank is n. So we're talking about just a square by square matrix, an n by n square matrix. A has n pivot positions. That's equal to saying the rank of the matrix is n.
Is that an if and only?
Yeah, so all these are if and only if. So if you know one, you know all of these other ones. So if and only if. Then, yeah, they're always if and only if.
Are we just expecting to kind of memorize or to think through them?
So that question was, it seems like there's lots of theorems with lots of information. Are we just supposed to have them all memorized or be able to think through them? Yeah, it's mainly be able to reason with them. We won't ask you to like write out word for word what the fundamental theorem of invertible matrices are, but you should know what these are and be able to reason through it. So, and any theorem that's named, you should probably know them. So if we said, you know, pick 3 things that are on the list for the fundamental theorem of invertible matrices. Pick 3 of those.
So what you're saying is like the theorems won't be written out on the test. We'll have to just know what they are.
Yes, the theorems will not be written out on the exam. So yeah, you'll have to talk them. So, but a lot of them, if you approach that by just trying to going through and trying to memorize all those theorems, then that's going to be hard. But most of the theorems are pretty straightforward if you understand what's going on. So there's a few that might not be, but like memorizing all the properties of the transpose, there's only probably 2 of those that you probably got to that might throw you for a loop. All the others you could reason through pretty easily, and that's true for lots of things. Like if you're just trying to memorize all these, you know, you can, but you really, if you understand what this is and when this takes place, then you're like, oh yeah, of course it's going to be an invertible matrix, you know. So yeah, building the connections, understand why all these would be true would be more important, and that will help you remember this. There was a couple hands. Never mind. They talked long enough that they forgot their question. So
Can I make a comment?
yes.
Since this is, I would like to point out that with all of these, since each of these are true if and only if, that means if something on this list isn't true, then it's automatically a non-invertible matrix.
They're either all true or all false. So as soon as you know one is not true, then they're all false, and so it's not invertible. So nice. Equation AX equals 0 has only the trivial solution. The columns of A from a linearly independent set. AX equals B has at least one solution for each B and Rn. Like we've already talked about stuff like this. Even before, you should have been able to reason through that at least these were equivalent. So, columns of A span Rn, you can throw that in. These are kind of all closely related. There's an n by n matrix C, such that you can do left multiplication and get the identity matrix. There's an n by n matrix you can do right multiplication by and get an identity matrix. We know that C and D have to be equal. That is the inverse. A can be written as a product of elementary matrices. We already talked about that. And A transpose is also an invertible. We're not going to take time. I picked one and did another proof that an invertible matrix times an invertible matrix is an invertible matrix. But we don't have time to go through that right now. Because we're going to talk about one way you can use invertible matrices, which is in cryptography. So this is an older method. It's not as reliable now. With computers, they can easily break these. So, but it is still kind of cool. Nice place to start on cryptography. So what do? You write down a message in letters, like I like to have fun. You translate the letters into numbers. So 0 is a space, A is 1, B is 2, etc. That's one thing you could use. And so I like to have fun. I is number 10, 9, something like that. 10. Space is 0. L is 12. Okay, so I can start translating those into numbers. Then I get an n by n invertible matrix, preferably larger than 2 by 2. I'll just use 3 by 3 as an example. And I split the numeric message up into packets. So if I like to have fun, I can write down the corresponding number beneath it, and including spaces, or you can cut spaces out if you want. And I take the first 3 numbers, and the next 3 numbers, and the next 3 numbers, and I put those into column vectors. And then I multiply each vector by the matrix to encode it. And then to the person I want to pass the message to, I pass them the encoded message and also get them somehow the matrix I used or the inverse of the matrix that I used. You don't want to send them together, because then if someone finds both of them together, then they can decode the message. Okay. Why do you have to use an invertible matrix?
Get the message.
Because otherwise, yeah, when you do that multiplication to encode, there's no way to get the original message back. So, so for example, if I did A, B, C, D, E, F space GH, I get these numbers. I'm using this matrix, which is the same one that you already found the inverse matrix for this as part of 1. I chopped up my 1, 2, 3, 4, 5, 6, 0, 7, 8, put it in here. So now it's represented as a matrix. And then I just encoded that by multiplying it by this invertible matrix. But since it's invertible, I can get this back. All I have to do is multiply by the inverse of this matrix times that, and I'll get this original message. So how would you encode this message? I take that. Oh, this is the one I already got, right? That's the one I just got right there. I already encoded it. So yeah, how do you decipher it? Well, I have the encoding message and the encoder matrix. Let's find the inverse and multiply. We're not going to take time. I have this is my kid's favorite message. This I think says something about have fun. In every prayer, they always pray that they can have fun. It's really important. So, but I'm going to show you how to do this actually on a spreadsheet. So, let me have this pulled up somewhere. So, anyone have a nice message for me to put in here? Doesn't matter, I can't type it anyway. There, let's have fun in LA. Drop the space. It's okay. I misspelled students in the last class. So it shows it's authentically from me if it's misspelled. So, all right, so let's shave fun in LA. So I have this set up. It already pulls up the numerical value of all those the letters, and then I put them here in this matrix. So this is my code matrix. So 12, 5, 20, 12, 5, 20, 19, 8, 1, 19, 8, 1. Okay. And then I took the encoder matrix and just multiplied that 3 by 3 matrix times all of that. And I get this thing. Now that's something I can pass. I give you that and the encoder, you can decipher that. You just have to find the inverse of the matrix. The inverse of the matrix, let me pull this up. you can Google Sheets or Wolfram Alpha or Excel, it will find inverse matrices for you as long as they're not too big. So if you do equals M inverse, so M for matrix, and then you just highlight the array. There you go. That's the inverse of the matrix. So that's what it took you. You can use that in the real world. Okay. We're testing other things in the exam, unfortunately. So this is a 215 technique. I'd love it if we could do more stuff like this. So, and then if you want to multiply, for example, this is to answer the third question from the problems of the day. This was a solution to a system where I had this times this. What does it equal? Well, I can do a matrix multiplication. It's M mult, and I take my first matrix, then a comma, and my vector or my second matrix, and go and multiply it. So some diagonal skills. And then to decode, I just multiply by the inverse, and then I get my Let's Shave Fun in LA back. So, and this is, I sent out an email. You get to do this for your assignment. I cut out 3 problems from the written homework on 3.3b. You get to create a message and encode it with the matrix and send it to someone else in the class, and then write up what you did. Okay. All right. Have a great day.
What are the chances?
Not everything can be, can it? But if it's invertible, it can be represented.
I forget why.
We do know that.